Okay, this is part 2 of today's lesson about nuclear decay. We've already done some of these kind of problems, but this will be a good review for you. And also I want you to look at the historical implications of some of these equations. Okay, remember when you're working these decay equations that the main idea is that the mass number on the top and the atomic number on the bottom on both sides of your arrow have to be equal. Right? Like a big giant equal sign. So you'll have to add up what's on the left of the arrow and what's on the right of the arrow and figure out what's missing. The first one, they give us 42K, but no atomic number for the bottom. But we can figure out what it is because the symbol is K. So you can look up potassium on your periodic table with a K, and then down here is the number 19. So that's 19. So 19 equals, top number, 42 equals 0 plus 42, and the bottom number is 19 equals minus 1 plus 20, and then what's atomic number 20 is calcium. So you just put Ca. Now we've done this one before. If you look at it carefully, what do you recognize as this particle right here? That's a beta particle, right? So this is the story of beta decay. It's what's happening in that equation. So if you were standing next to this potassium 42 and it's giving off beta rays, beta particles, you'd want to get away from there because that's radioactive and that's dangerous. Okay, the next one is 239 Pu. Let's look that one up. That has atomic number 94. So now we're ready. 239 equals 4 plus 235. And on the bottom, 94 equals 2 plus 92. What do you know is number 92? Uranium. So this is plutonium-239 giving off what kind of a thing is this? That's an alpha particle. That one is beta, and that one is alpha. And between these two, which one is more penetrating? Did you say beta? That's right. Okay, this one you can figure out. Let's look at number 4. On number 4, 1 plus 3 is 4, and the bottom number is 1 plus 1 is 2. What's 4 over 2? He. Now this could be just a proton, but they didn't put any symbol up here, so we don't really know if this is a hydrogen atom or a proton. And this is hydrogen 3, which has a nickname of tritium. And notice what's happening is we're putting these two small things together to make one larger thing. These other decay equations were like decomposition, so the parent isotope is breaking down like a decomposition reaction. But this one, it looks like a synthesis reaction because the two smaller isotopes are coming together to make a larger one. So this is a different story. This is the one you should be working on your Venn diagram. What's happening here? This is nuclear fusion. Hopefully your Venn diagram research is going well with that.
This is Larson's on right now.
Okay, great. I'll meet her name.
Oh, did Karen say that was okay?
It's okay. I can scrub it out.
Okay. Yeah, I'll be in there.
She's on her. I told her to send her down.
Now this one, number 9 here, this is a special historical importance. See if any of you recognize that one. This one has some historical importance of what's going on in the story. You add it up the same way, so you'll have to add up the top and the bottom numbers. Over here, the thing that's a little different is the 3 in front. This is a coefficient. It means 3 neutrons. So you have 3 times 1 for the top number and 3 times 0, 0 for the bottom number. And then you do the problem like always. Let's see if you can recognize what this is when you get it done. I'll give you a hint. That has something to do with this. Also, I want you to notice that in these kind of equations where there's like 2 reactants and between 2 or 3 or more products, this is a special type of artificial radioactivity. So this is the target. This is the bullet or the projectile. So they've got a big isotope and we're shooting neutrons at it.
And I had to make a guess.
And then these are products. And then these are ejected particles. Okay, and so just like it sounds, if you took your gun to the gun range to go shooting, because you know we live in Texas and everybody has a gun, right? If you take your gun to the gun range, you have a big target and a little bitty bullet, and then after you fire your gun, you have your big target, but now it has a hole in it, so it's a little smaller than it was before, and there'll be some little fragments of your paper target that go flying. So that's what we have here. The target is the biggest thing. The bullet will be small, and those are on the reactant side. And on the product side, we have products which are still kind of big, but smaller than the target was, and some ejected particles that are given off. This one is also significant because notice that this one neutron here, it takes one neutron to make this reaction occur, and then that one neutron is able to give off 3 more neutrons at the end. So this is kind of like, you know, you have a secret and you tell one friend and they tell 2 friends and then they each tell 2 friends, and before you know it, the rumor is all over Westlake. So this is also something that repeats, that one neutron it takes to cause this reaction to happen, but it gives off multiple neutrons at the end. And then each of those separate neutrons can go do this reaction over and over again, and it can become a chain reaction. Okay, so what do you need to accomplish today? Today's assignment, you're here. You need to make sure that you have finished your Venn diagram and turn that in. You need to take the tour of the nuclear power plant. I gave you 3 possible websites. You can pick one of those or find a different one of your own. I thought it might be easy for you to print a diagram and then annotate it, I guess if you're printing at home because you can't print from school. If you find that too difficult, then you can just draw a diagram, or you can look in your chemistry textbook. I think it's chapter 25. There's a diagram in there that you can draw and just copy it down. But I want you to annotate it, so you know, draw little arrows and say what this part is and what that part is and what does it do, what is it made out of, like that. And here's the important part, what I really want you to find out: can this nuclear power plant blow up like a bomb? And how much does it cost to build? This is very important that we consider this technology because we're in an energy crisis and we're always looking for better, cleaner, cheaper sources of energy. Well, can we look at nuclear chemistry as an alternative, and can nuclear energy make a comeback? We need to find out what safety regulations are required. Is it safe to live near a power plant? And which one is the closest one to us? So these are what you're investigating: your Venn diagram, your tour of your nuclear power plant. Those are both due on the 22nd and the 23rd. Feel free to turn them in as soon as you get them done. And then you need to finish up your decay equation sheet. And if you didn't already finish your half-life worksheet, you need to finish that too. The presentations that are listed here on your sheet, don't be a panic. I haven't given that to you yet, but I will. Good luck today.